Hey, good afternoon, everyone. Thank you very much for organizing this workshop, and thank you for giving me the opportunity to give a talk. I would like to bring you to the lower crust, which is probably the least understood part of the lithosphere. And I would like to do that in two parts. The first is focusing on Tibet, on which I mostly work with French people. And the second part is on the Alps, on which I mostly work without French people. And I know some of you are jet-lagged and getting tired towards the end of the day. So on the second part on drilling project, there's a flyer here, and you can take it later to ask questions. My talk is also about collision, as Rob's talk, but it's only about tectonic collision and not institutional collision. Although it could have happened, because I did my PhD at ENS Paris, just up the hill from here, and a rumor at that time said that if you work on Tibet, you better work with Paul Tapponnier and consult him at some point. And I sort of ignored this rumor until the very last year of my PhD thesis, or almost the last month. And before the defense, I came here with my supervisor, Jérôme Vergne, who is here on the left, to show Paul my main result from the thesis, which is this profile. It is a receiver function migration profile. Rob already explained you what receiver functions are. What you see here in red is not velocities, but velocity changes with depth. And basically what you see is how the Moho from the south in India gets deeper and deeper below southern Tibet and gets flat again in southern Tibet. And moreover, you have this second interface following the Moho there. With further data, our interpretation of this layer is that this is the lower crust of India, which underthrusts the Tibetan plateau and gets into eclogite facies metamorphism, and that's how you develop a second interface, a second impedance contrast also on top of this layer. And what is interesting is that the limit of the Indian plate is actually much further north geographically than the geological limit of rocks on the surface from the Indian plate. So it's decoupling between the deep processes and the surface processes. So that's all fine. The reason why this could have led to institutional collision, and Jérôme was very stressed at this meeting, is that this is the model of the time that Paul has published a couple of years before. And here you see that there is direct subduction on the southern side of the Tibetan plateau, and our data show that there isn't. There is actually continuity of underthrusting with this layer for about another 250 kilometers horizontally. So explaining this to Paul in detail and expecting some reactions, surprisingly, there's not a harsh reaction. He was listening very patiently and silently, and then in the end he was smiling and nodding. Okay, so you have an eclogite pillow there. And he was calling this layer of 200 kilometers long and 15 kilometers thick of eclogite as a pillow, and I wanted to tell you this anecdote of those times. Why is this picture important? We can spend a lot of details on the resolution capability of receiver functions, the role of density and rheology. We can come back to the amount of melt in the upper crust at another time. Today, I would like to more focus on how geophysical imaging and modeling can track metamorphic phase changes of the lower crust. And for this, we have built a joint model with many elements based on the seismological image, which was giving us the geometry. In the model, we were combining three different elements. The first was a thermokinematic model, which is simulating the collision between India and Tibet, and providing us the temperature field and the pressure field in this area. To this model, we have coupled petrogenetic grids. These are basically databases in which, as a function of pressure and temperature, you can calculate the stable mineral assemblages and associate the appropriate density to those rocks. And coupling these densities to the right PT conditions in the model, you can build a density model and compute the gravimetric response in a synthetic way, which is the red line, and compare it to the data across the Himalayas and Tibet, which is the black line. So what can we do with this kind of joint modeling? For the lower crust, I have to say that we have tried different grids, and the composition was the same. It was average lower crustal chemistry from Radnik and Fountain, but we tried three different water contents. The first was a fully hydrated model in which all the water is there to produce all the hydrous phases, and you can recognize from density all the major metamorphic facies, blue schist, green schist, amphibolite, granulite, and eclogite with high densities. A second model was a partially hydrated model in which the limited amount of water made garnet stable at lower temperatures. We have high densities already at quite low temperatures. And the third model was a dry model. The previous would be amphibolite. This would be a granulite model for the lower crust, in which the garnet is even at higher concentrations and making higher densities. So we tried out these three models, compared it with the gravity data. And as you can see on the right, the wet model and the dry model are completely off of the gravity data, which is in blue. Only this partially hydrated model is fitting our long-term far-field difference in the gravity data. But even in that model, you have a discrepancy in the middle part, which is the Himalayas and southern Tibet. So we need to do something more to have a good fit. And until now, all the reactions in the model were assumed to take place at equilibrium conditions, so directly reaching at the PT conditions. So what we played with in the second phase is to see if the reaction is happening maybe in a slower way. This is the densification of the lower crust, or it's maybe even hindered for 300 kilometers and then getting dense in a very rapid way. And so it turns out that out of the three models, equilibrium, slow kinetics, or overstepping, kinetic hindrance, it is the one with overstepping that explains the gravity data. How is this possible from a petrological point of view? Well, if you look again in cross-section, the lower crust is getting dense at point B instead of point A. And to understand that in a PT space, this is the path of the lower crust. And the reason for not having the reactions at point A is that because the rock is nominally dry, all the hydrous phases are inside the minerals, and you can overstep the plagioclase out reaction, which is this gray line. So the lower crust is basically metastable for about 300 kilometers until reaching point B. And in point B, you hit the dehydration line. To the right of this line, you have free water. All the reactions catch up very rapidly. So equilibrium does happen here. Plus, you have a localized microseismic activity to account for the volume change at those depths for the lower crust. More recently, we have revisited the question of the rate. How steep is the line of the reaction rate during the postdoc visit of Hetényi in Lausanne? And we played with the slope and the location of this reaction line in the model space. We compared this with, again, with the gravity data, trying to find the best fit in terms of reaction speed and location. And once we found that, we found quite a large range of reaction rates. We try to compare this with what petrologists find for reaction rates on a small scale, from outcrop scale or even lab and experiments. So this diagram on the right is showing you two groups of metamorphic reaction rates. On the top, you have the fast reactions with lot of free water and typically contact metamorphism, which are orders of magnitude faster than regional metamorphism with much less free fluid in the field examples. These are all the small scale estimates, and our estimate from 10 kilometer to 100 kilometer scale is the red box, which fits very well the regional metamorphism. So we are very happy because the very small scale and the very large scale estimate fall into the same box. And this was causing us some satisfaction and making us happy. And if you would like to see more happy results, you can come to the poster of Rodolphe tomorrow from a happy country, the Bhutan Himalaya. So it's all nice, but people usually then ask questions. Where is your representative rock sample to do this kind of lower crustal model? Well, we don't have such a sample because it's so deep in the crust and we don't have an outcrop of it, so we cannot assume really other compositions. We could simulate other things, but we thought that having just the average lower crust is just fine enough. Another question that typically comes is, what is the benefit of using seismic arrays if you don't have those samples? I believe that having large seismic arrays, especially in 3D coverage, as the one we have done over the Alps in the past 10 years, with 600 broadband seismometers listening to the area, is actually very valuable. You get a lot of interesting information on this wave speed and also the structure of the collision zone. And of course, you need to compare this with rock physics data. And I think the next talk tonight, we'll talk about more that in the Alps on the French side. Nevertheless, after this large-scale past history, I ended up working on smaller scales because I really wanted to see a bit more what the lower crustal rocks look like and what is the structure of the lower crust. And for that, I invite you to come to the Alps. And some of the better maps of the geology of France, you can actually find this place, which is in Italy. Currently, you are sitting here. This is where I work in Lausanne. And in a straight line continuation, you come to the Ivrea-Verbano zone, which is the Southern Alps, not far from Milan and Turin, in the Italian side of the collision zone. This is the current geological map. You see the plate limit between Europe and Adria is the insurbic line, which is supposed to be geologically dead. And this is the outcropping Ivrea-Verbano zone with all the lithologies of the upper crust and the lower crust. The history of this zone is that in the Permian times, you have had various phases of magmatic intrusions from the bottom through the middle crust and the lower crust. Then you have had Jurassic extension, thinning the crust and bringing the units closer to the surface. And finally, during the Alpine collision, all this middle to lower crustal section was turned 90 degrees, brought to the surface. And so today you can walk through the crust or drive through the crust from the surface volcanoes to peridotite outcrops in the Alps in a very continuous manner. Well, this sounds very good, but the outcrop quality is very bad. Everything is altered, highly vegetated, and very steep. So we don't have a good record of this continuity in our archives. And this is why we wanted to create we did create a large collaboration of a drilling project, drilling the middle crust, drilling the deep crust, and drilling through the borehole. And the first two boreholes have actually already happened. This is part of Project Dive, which is standing for drilling the Ivrea-Verbano zone. Here you see a perspective view of the middle and lower crust. Our two boreholes in Ornabasso and Megalo have been drilled in 2022 and 2023-24. There's a lot of collaboration on this, especially from petrologists and geophysicists, but also some other fields like microbiologists looking for extremophile bacteria. France was represented by the Grenoble group looking for fluids and gases. And what is very nice is that these two boreholes, which have reached 600 and 900 meters depth, are fully cored. So you have 1.5 kilometers of drill cores, which you can analyze in the lab for all kinds of methodologies. Both boreholes have been logged with various borehole logging techniques. So we have a very rich data set at the surface and also inside the hole. Now I would like to show you a couple of impressions of the project and the first results which are coming out. This is our playground. You can see our chief on-site geophysicist, Andrew Greenwood, at the small rig, the medium rig, and the large rig, which is not very large, but very strong. And sometimes you have big trucks. And when the big truck gets stuck in the mud, you have the even bigger truck coming, and all kinds of adventures and challenges that you have to solve. When the drillers are at rest in the evenings and weekends, then we do the borehole logging to get all the data, no matter what the weather conditions are. We have a nice big winch, which is able to log at very low speed to get high resolution data. Our engineer, Ludovic Baron, is doing great work on this, and we have really acquired good quality data on that. Now, coming to the results, this is the lithological summary of the two boreholes, of the middle crust and the lowermost crust. And the first thing you see is a very strong spatial variability of the lithologies in these two holes. This striped diagram shows that the lithologies change all the time. The middle crust is typically composed of metasediments, amphibolite phase metasediments, and metamorphics. And the lower crust is mainly composed of mafic rocks, so gabbronorites, gabbros, another type of metasediment in granulite facies, and a few other lithologies. We haven't touched mantle rocks, but we have touched a lot of lithologies and a lot of variabilities. And just to show you my favorite core, in this 1 meter section of core, we have 4 lithologies changing every 20-25 centimeters. So the variability is really extreme at a scale that we have not expected. The lower crust can be very colorful, and you can see a lot of different deformation patterns, both tactile and brittle, including pseudotactile cataclysite and other interesting features. The borehole logging data was very interesting because thanks to the continuous logging, we could use those data to recognize our main lithologies. The two most useful data sets was the gamma ray and the magnetic susceptibility data. And if you do a cluster analysis of these two data sets, which is here, you can define 3 clusters basically on just the data alone. And it coincides or corresponds very well to the main lithologies that we have, which are the metamorphics and the metasediments So basically, the borehole log is a very good proxy for the lithologies that we have identified in the borehole. Once we have the data from the borehole for seismic wave speeds, we try to do the exercise of upscaling again to large scales. And this is a map from a geological map of the area. We try to synthesize this into a 1D lower crustal model of amphibolite and granulite facies rocks, and associate with each of these layers a random velocity that fits that kind of lithology, and then try to simulate what is the large-scale response of such a velocity profile. And what we see from this analysis is that there is a significant effect of anisotropy because of the metaphilites really cause several percent anisotropy of these rocks. And so if you want to use the data to estimate MOHO depths, you start with a minimum of a 1 kilometer accuracy problem, which is not related to the data set itself, it's related to the methodology, how you get the MOHO depth estimates. In the same way, if you want to estimate the silica content, how felsic or how mafic is the lower crust, you are bound to a couple of percent of error compared to the thermodynamic estimates. So we have to update the approach, how we estimate this kind of property. Another physical parameter, which is very often used in geophysics, is the density of the rocks. Here are 3 examples taken sort of randomly from the second borehole. Each of them have a density of 3.2 grams per cubic centimeter, so very close to the mantle density, which is 3.3. And generally, people could ask, and this is the full log of densities of 900 meters of cores that we have scanned in the multi-scanner core logger. And you see that beyond some uncertainty, we are between 3 and 3.2 grams per cubic centimeter density all across the lower crust. So people may ask, is this already part of the MOHO transition from lower crust to mantle? For the geophysicists in the project, the answer is yes, we are close enough. We are in the transition to the mantle. For the petrologists, not necessarily, because they can imagine a variety of high velocity, high density rocks, which could be ultramafics of garnetite, but not yet part of the mantle. So we have a discussion ongoing of how to interpret this data set. One of the interesting projects within DIVE is to look at the thermal properties of the lower crust, because we have very limited information on how the temperature field is in the lower crust. And to do that, we have 2 types of analysis. One is a thermal conductivity scanner of the cores. So we can scan thermal conductivity at a millimeter or centimeter resolution. Here is a 0.5 meter piece of rock, and here are the values that we measure. The mineralogy directly impacts on the value of thermal conductivity. And the second measurement that we do is to measure the radiogenic element concentration using gamma spectrometry on powder and also spectral gamma borehole logging. And once you have all this data, you can build thermal models of the lower crust and do calculations how the variability of low TC and high TC and low radioactivity, high radioactivity rocks affect your heat flow estimate. And this is work in progress, but we can already say that the uncertainties increase by a lot if you consider these variabilities. So in summary, the 2 communities in the project, geophysics and petrology, discussed already a lot about the lower crust and how close is the crust mantle boundary to the MOHO. The first thing we can say is that the spatial variability is really impressive. The scales are much smaller than what we get from seismic wavelengths, even if you do active seismics. And we still need to find more about the correlations and the causality between mineralogical composition and the wave speed. How close is the MOHO, which is a geophysical definition, to the crust mantle boundary, which is a petrological definition? The answer for petrologists is that it depends. It depends on the water content, depends on the history of the area. For the geophysicists, the answer is they are reasonably close. It could be as little as a few hundred meters from each other, which is little for geophysics, but maybe a lot for petrologists. We found that there is an inherent gap in the scales of investigation between what we see in the outcrop and what we see in geophysical results. And with this in mind, we are now planning the 3rd borehole in the project to go to Alsacia. In Alsacia, we have a lower crustal unit and 5 kilometers of peridotite outcropping directly from the mantle. This is the famous Balmucha peridotite, so we have already good gravity and seismic data to investigate this area. And we have beautifully outcropping fresh, unaltered peridotite, on which we hope to do some experiments on fluid-rock interactions, including hydrogen, including CO2 experiments in the future. This is the current progress, more to come in the coming years, and I would like to leave you with an artistic drawing of how the lower crust looks like. Thank you.